we have a great program, and I'm looking forward to it tonight. Our speaker is going to be Sherwood Richards. He studied at the University of Virginia, got his PhD at Caltech, so he did some work there, I'm sure. But California, it's a good time to be in California, not now. Okay, he did research at North Carolina State University and the University of California, Berkeley. Then he joined the University of Tennessee as a faculty member in 2023. He's currently teaching in undergraduate astronomy and general relativity. Sherwood's research is focused on quantum mechanical processes driving changes in neutrino flavor and explosive astrophysical environments. I think that means supernovae.
And neutron star mergers.
And neutron star mergers. Black hole mergers? Maybe not.
They're not so explosive.
Yeah, okay. He has other research interests, quantum computing, machine learning, and gravitational waves. They're doing great quantum computing at Oak Ridge. Are you working with those folks?
Yes, I am.
Yeah, that's, do you work with Warren Grease?
No, there's a group with Inseng Su. No,
Okay. That can be another talk.
Yes, absolutely.
Once we get speakers, we hold on to the speakers. Okay, I look forward to your presentation, Sherwood. And if I refer to him as Mr. Forrest, it's because I used to watch Robin Hood. It confuses me. Okay, glad you're here.
All right, thank you very much.
Please clap for him.
And so I am actually the Sherwood III, and my grandfather was named by his siblings after Sherwood Forrest because he was the youngest of 10. His siblings were reading Robin Hood at the time, so that is actually where it comes from. All right, well, thank you very much for having me here today. So I'm going to talk about some of the stuff that I find exciting about my research. I've never talked to this group before, so I don't know who everybody in the audience is. So hopefully there will be something for everybody. This is a lot more fun if people interrupt. I love it when people interrupt and ask questions and argue. And so if there's anything that you want to talk about, ask about, please just interrupt me. And I will try to keep time so that we don't stay overnight. But okay, so yeah, my name is Sherwood Richards. I'm a professor at UT Knoxville, and I study a lot of the microphysical processes that happen inside of core collapse supernovae and neutron star mergers. So really the focus of my research, the thing that differentiates me from a lot of the other people doing supernovae at Oak Ridge and UT, is that I focus on the quantum mechanics of a particular particle called neutrinos. And I'll talk a little bit about that, but before we get into that, I think I'll just talk about some of the, I think the thing that gets most of us into explosive astrophysics, and that's the actual explosions themselves. Okay, so starting off, this is a beautiful picture of the night sky. When we look at the night sky, it's serene, it's calm. We think that it's been there for ages, so we are tempted to think that the night sky is not changing. But that's actually quite far from the truth. If you look closely, there's constantly things happening. And so this is an example of the most famous supernova to date. This is supernova 1987A. This was the most recent nearby supernova, so that's within our galaxy or nearby dwarf galaxies. And that was in 1987. And so myself and many other people around me are anxiously awaiting for another one of these things to happen sufficiently close by that we now have techniques to study these in much greater detail than we were able to previously. Now, supernovae, the ones this nearby that happen within a few kiloparsecs, or a few tens of thousands of light years, are very rare, maybe 1 or 2 per century. But they're actually, if you look at other galaxies, they're happening quite regularly, and they're observable with amateur astronomical equipment as well. You can, I don't know, maybe this is something that you guys already do, but you can look up databases of active supernovae, where they are, how bright they are, how quickly they're growing, and you can observe them with pretty straightforward equipment. Now, there are a few supernovae that are quite exotic. There are some supernovae, many supernovae behave similar to each other, but really all that we get is this little blip of light. This is 3 images taken at different times, and we don't really see that much. We don't see the supernova exploding. We don't see things flying around. We always see is a bit of light, it gets bright, and then it gets dark again. And based on that, we have to infer everything about the dynamics of the explosion, the extreme physics happening deep inside that we can't see. And so my job, and the job of many other people in the field, is to try to map that little change in light to all the extreme physics driving this explosion, and to understanding how this explosion leads to the evolution of the universe, how the universe generates the elements like gold and platinum and carbon and iron, all the things that make up the world and the things that we care about. All from this little blip of light. So in order to understand astrophysical explosions, it might be instructive to first go back down to Earth and try and understand something more terrestrial. So this is an example of a firework, a commercial firework. And so the way that it works is there's the fireworks inside of here. You stick it inside of a tube, you let it on fire, and so the fuse, the spark goes from the fuse, and first the spark will light the powder down here, which explodes and causes the firework to shoot upward. And then the fuse will burn slowly until it gets to the center, and so there's some time delay, and it explodes. Another type of explosion is a nuclear weapon. These are the most powerful explosions that we have been able to generate here on Earth, and they operate a little bit differently. So this is an example of a diagram of one kind of nuclear weapon. The idea is you have a bunch of high explosives on the outside and a radioactive material on the inside. And you set off these high explosives so that they compress the radioactive material in the center, and that causes that radioactive material to become dense enough that these free neutrons cause a chain reaction that suddenly releases a huge amount of energy. And so this is the famous Trinity bomb at Los Alamos. The chemical explosions like fireworks are something like 0.0000001% efficient. So that if you're looking at the amount of energy in the firework itself, the max amount of energy that you could possibly extract just from Einstein's equals mc squared, and you compare that to the amount of energy in the actual explosion, it's extremely inefficient. When you have something like a nuclear weapon, it's still quite inefficient, but it is much more efficient than chemical processes. And it turns out that the astrophysical explosions are even more efficient than this. Okay, so based on what we know about explosions here on Earth, how can we understand what's actually going on inside of this star that's 21 million light years away? We can't see the star, we can't see inside of the explosion, we can't see anything after the explosion, all we see is that little bit of light. Now, because 21 million light years is a very long distance, this tiny bit of light, if you map it, if you look at the material that's exploding and you map the amount of light that we see, multiplying it by the relative area of the, if you take into account the fact that it's very far away, this means that this is a giant explosion. This is a huge number. I don't even know how to say this number. Much larger than the largest explosions we have generated on Earth. This is impossibly large for anything that we could hope to do. Yeah, how many zeros are there? 3, 6, 9, 12, 15, 18, 21, 24, 27, 28, 29 zeros. All right, so there's not just one way to do it. Turns out that nature is incredibly diverse, and there's rich phenomenology, and there's many ways to do this. But you can sort of classify all of these, what nature does. To create an explosion, you need these three ingredients. You need some source of energy. You need to bring all of that energy into some small area. And you need some spark that suddenly causes that energy to be released. So let's do some practice. In the case of regular fireworks, the source of energy is this chemical binding energy. So we have a bunch of chemical bonds in here, and there's energy, potential energy stored inside of these chemical bonds. When you light that spark, you cause some chemical reactions that release that binding energy, and so the energy is confined inside of the shell. And if you were to just have a bunch of this powder and you were to light it, it would make a nice poof, but it wouldn't be an explosion. It's the fact that it's contained inside of the shell that turns it into an explosion rather than a deflagration. Then, of course, lighting the fuse is the spark that sets everything off. And then, you get a nice explosion. In the case of nuclear weapons, the source of energy here is nuclear binding energy. So just like with chemical bonds, there's potential energy stored inside of nuclei. And if the binding energy in the final state of your nuclei is larger or more negative than the binding energy in the initial state, you get this extra energy from this reaction, and you do enough of these nuclear reactions that you release a huge amount of energy. You confine the energy, so in the case of the nuclear bomb we're showing here, you compress it all together with these explosive charges, and then you create a spark, which in this case is radioactive neutron emission. So these processes release neutrons, and more neutrons collide with radioactive nuclei, which releases more energy and emits more neutrons, and you create this positive feedback loop. So this is terrestrial explosions. Yeah, so you get a huge nuclear explosion. All right, so like I said, there's a number of ways to do this astrophysically. So let's talk about what those actually are. So just like nuclear explosions on Earth, nature does the same thing, just on a much grander scale. So if you have many elements that store a lot of nuclear binding energy, and you confine all of those atoms together, nature tends to do this with gravity. And you set off a spark, which can be matter accreting down, so matter falling down onto this sphere of material ready to release its nuclear binding energy. When you have material fall, it gets hot. Or if you have two of these stars collide with each other, you can suddenly generate a lot of heat that sets off these nuclear reactions. This is one example. So this is an X-ray burst. You can have nuclear material sitting on top of a neutron star with an accretion disk around it that's just sucking matter off of a nearby star. Eventually, you build up enough matter on the surface that when you start the nuclear reactions, there's a chain reaction, and you set off an explosion. You can also do the same thing. There are a number of models of type 1A supernovae, so these are thermonuclear supernovae. One of them is that you can have two white dwarfs, and these white dwarfs orbit, and once they collide, there's enough energy there to start these nuclear reactions, and you can get a type 1A supernova. And this is an example of a type 1A supernova. Again, this is just a blip of light. There is more information than just the light. We can look at the frequencies of light. We can look at the polarization. We can look at spectral lines. But at the end of the day, this is one of the ways that we generate these incredibly energetic explosions. All right, but that's not all. There's nature is very creative. Okay, so let's say we have nuclear binding energy. We once again confine it with gravity, but this time there's a different source. We can, with high energy photons, you can start nuclear reaction processes that that actually, so this is a hypothetical type of explosion, so the idea is you have massive, massive stars that can only exist early in the universe because you can't make these gigantic stars, something like 100, 200 solar masses. Given the amount of metals, so anything other than hydrogen and helium, that's in the universe today, you can't make stars this big. But in the early universe, you can. And so you can make these 100 or 200 solar mass stars, and in the center, you have so much pressure that there's so much kinetic energy in these atoms that are bouncing around. You create these very high energy photons, and so you can convert some of this mass energy into photons, which will cause further dissociations and nuclear reactions. And you can this can cause a pair instability supernova. This is a hypothetical type of supernova, something that has been simulated, something that is reasonable by anything that we can, it's theoretically sound, but we have never observed this. This is one example of something that I think is so exciting about theory, because we can predict this sort of thing. We can put all of the physics that we know about nuclear reactions and gravity into these simulations and say, this is what we expect. But we need new observatories, like JWST might be able to observe something like this. So this is one of the mechanisms in astrophysics that we hope to be able to detect, but has not been detected yet. All right, so things in general, everything has some amount of rotation. If you have enough rotation, you can have a lot of energy stored in this kinetic energy. And so if you have enough of this rotational kinetic energy, and you can confine it together strongly enough, again, with gravity, and you cause something to collapse in a way that you can extract this kinetic energy, then this is another potential source of energy for astrophysical explosions. This is a simulation that we did a number of years ago. This is what we're showing here is the strength of the magnetic field inside of a collapsing star. So let's see, can I restart the video? So this is a massive star that was originally something like 20 solar masses. So it lived for several million years until it got to the point where it was about to collapse. It suddenly collapsed because it was rotating so quickly. When it collapses, you have this conservation of angular momentum, and so it quickly, the rotation quickly increases, and because it's rotating so fast, you stretch the magnetic fields, and so you end up dumping a bunch of the energy from this rotation into these extremely strong magnetic fields that create these structures. So this is still deep, deep inside of a star's iron core. This is something like maybe 200 kilometers or so. So it's really just a small region inside of the core just as the explosion is launching. But this shows a mechanism by which, so you have very rapid rotation, which is winding up these magnetic fields. And the magnetic fields you can see as the strong magnetic fields form these flux ropes, and you sort of they kink up and cause these polar explosions. So this is the rotation axis. So it's zipping around very quickly this way. This is quite exotic. We don't actually know how we can get stars to rotate this quickly, but this is potentially a way that we can explain the most energetic explosions in the universe that we can't explain by the other mechanisms that I mentioned so far. Is that a question? Yeah.
The early supercomputer models of supernova, they often, at some point, couldn't get them to explode until they included asymmetry and rotation.
Yes. Yeah, so there's a fun history with core collapse supernovae, and it's always going back and forth. So for a long time, so the first models of supernovae, so this is back Sterling Colgate and I forget his first name, White. Colgate and White had a theory for supernovae. This is back in like the 60s. And they put in neutrinos into a collapsing star, and they were able to explode. These are some of the earliest supercomputer models. When you actually do the physics right, you do everything. You put in all the neutrino radiation, general relativity, nuclear equation of state, all the most advanced physics that we know. You put it into 1D models, doesn't work. No explosion. So this was a big problem for several decades. Back in the 2000s, people said, well, maybe we need asymmetry, so you do it in 2D. And so you get some of these interesting asymmetries, and you get some features of turbulence. And those simulations exploded. And so people were excited, like, we've solved the supernova problem. Until in the 2010s, people started saying, well, you know, nature's not 2D, nature's 3D, so we do it in 3D. And you run those, you know, they're extremely expensive supercomputer calculations, and they don't explode. So fast forward to the 2020s, and now there are several groups doing 3D core collapse supernova simulations. Some of them don't explode, but some of them do explode. And so the upshot is right now that the theory appears to be consistent with supernova explosions occurring based on the physics that we know. But that's some kinds of supernovae, and these supercomputer models still have some very large uncertainties that still need to be addressed. There's not a good mapping between the simulations and what we actually observe. So yeah, it's an exciting, constantly evolving field that's rich in many of these details. It depends a lot on poorly understood extreme physics and extreme environments. It depends a lot on the interior structure of stars that we don't know because we can't see inside of them. So yeah, there's a lot of things going on. Yeah.
So you're proposing these hypotheticals. What are the artifacts one would look for today that can say, yeah, this is true?
Great question. So, no, I won't. Well, I mean, I'll talk about it now. So one of them is we expect a large amount of asymmetry. And so this is a mechanism where if you wind up magnetic fields strong enough, you can, depending on the circumstances, you can launch a bipolar jet. There is a connection between long gamma ray bursts and these extremely energetic supernovae. And so it's thought that they're of a common origin, and this is potentially a mechanism that can explain both. So you can also look for things like signatures of nucleosynthesis. So you do these kinds of calculations, and the thermodynamics for material ejected in these directions is going to be different than the thermodynamics of material ejected in these directions. And so you form different kinds of elements, and you can look for those signatures, assuming that we understand the nucleosynthesis, which means that assuming that we understand the properties of these unstable nuclei that are forming well enough to actually do that calculation. So there's a number of observables to connect to it, but I think that the theory and the experimental knowledge of like how this physics works are still very much coupled and still very much kind of moving, leapfrogging each other. So, yeah.
You're showing these spiky patterns in two directions. Is that the beginning of simulation of a jet?
So this is actually the first magnetorotational supernova done in 3 dimensions. And so 2-dimensional simulations showed a very strong jet. Just it shoots, pierces straight upward. Yeah. But this one doesn't. It shows that if you actually do it in 3 dimensions, there's a physical instability causes to crumple up, and so there's.
So what are the spiky?
Those spikes. These are numerical artifacts. Numerical artifacts. Yeah. So they follow the general direction of the magnetic field, but really it's just the simulation code isn't perfect, and it's hard to visualize it.
Predicting the cosmogenic jets emitted in 2 directions.
Yeah, I mean, so well, we kind of broke that. Yeah.
Are you saying that this one didn't ultimately become a supernova?
It hasn't been run long enough to say that that actually exploded. So supernovae take, the engine takes seconds to build up enough energy. This was run about 200 milliseconds before it just becomes too expensive to run. So yeah, you don't actually get all the way there, but you get a huge amount of energy, like the amount of energy that's contained in these ejecting lobes is increasing, and it hasn't stopped increasing by the time that you run out of time. So yeah, we need bigger computers. Okay, and yeah, so this is one example of a famous hypernova, supernova 1998 BW. And so this is a hypernova, just means a supernova with an extreme amount of explosion energy. You need that extra energy from somewhere to drive something this energetic. Okay, lastly, the canonical supernova picture says your ultimate source of energy is gravity. You can find that energy with gravity, and photodissociation, so that is high energy photons breaking apart nuclei, sets off this collapse. So this is the common story of how core collapse supernovae work. I'm sure people have heard it before. Massive star collapses, and then you get a supernova. Now that story, how you get from gravity pulling things inward to gravity exploding things outward, how does that make any sense? And so this is a really interesting problem that we'll talk a little bit about. But in order to understand that, we need to, I just need to make sure that we're on the same page regarding some particle physics. So this is everything that we know about particle physics. There are quarks, so the up and down quark make up all of the nuclei the regular nuclei that we're familiar with. There are heavier ones that we don't really see very often. There's also 3 leptons, one of which is the electron. We see this one often. These ones we don't see very often. And there's 3 kinds of neutrinos. And these are the key players. Neutrinos are strange, but they're the key players in explaining how this collapse leads to an explosion. If you look at your fingernail, it's maybe a centimeter by a centimeter. Right now, there are a number of photons, or a number of neutrinos going through your fingernail, coming from the sun. Does anybody have any idea how many are going through your finger every second from the sun? That's a good guess. Yes. We can't see the sun. It's nighttime. The neutrinos are going through the Earth and through your fingernail. The neutrinos created inside of the sun, they pass through the entire sun without interacting with anything, and then go through the entire Earth and then through your finger. Day or night, just they interact so weakly that it passes through everything without colliding. Now, you might say, well, that's a nice story, but you're just making that up. So how do you actually know? Well, in order to see neutrinos, they interact so rarely that if you have, it's not like photons where if you'll see it, you have some detector in your eye that the photon hits your eye and you register some kind of signal. Because neutrinos just pass through, so you wouldn't be able to see it. In order to see it, you need to set up a huge volume of detector so that in a rare event that a neutrino hits something, you can see it. So this is Super Kamiokanda. It's a neutrino detector in Japan. It's empty right now, but they fill it up with water. And all of these things lining the outside, these are just photomultiplier tubes. So the neutrino hits the water, and that emits light, and the light gets detected by these cameras effectively. And you need a huge amount of water because these reactions it's so rare that a neutrino hits anything. Neutrinos are the key to understanding how stars actually explode. So let's go through what that looks like. So if we have a very massive star, something that's at least 10 times the mass of the sun, it will look something like this. So this is Betelgeuse in a representation of Betelgeuse, which is a red supergiant star. And it's superimposed on a diagram of the orbits of planets in our solar system. And so this orbit here is Jupiter. So this is just showing you the size of a red supergiant star. These stars will last for millions to tens of millions of years, burning their nuclear fuel, building up a denser and denser cores. So they start out as mostly hydrogen, they form helium, carbon, oxygen, neon, until they start forming iron. They build up an iron core. So this is a zoom in the very center, 1,000 kilometers or so. This is showing various quantities. Let's see. So this one right here is showing the abundance of iron. So out to 2,000 kilometers or so, you have this dense iron core. So after millions or tens of millions of years of burning and slowly building up this internal structure, and this is just about real time, it collapses in about 1/10 or 2/10 of a second. And so what's left over is something that looks kind of like this. So if you let it collapse and for maybe 0.3 seconds, and then you hit pause, it will look something like this, where that iron core is still all around here. So it's still collapsing inward. What you have is a protoneutron star. So this is something that's eventually going to become a neutron star. You have a shock front here, which is where the supersonically infalling, the rest of the star is infalling supersonically. It hits the shock, and it falls down and settles onto this protoneutron star, building up the mass that's eventually going to become a neutron star or eventually a black hole. So all around here is the iron core of the star, which is falling inward, and somehow through all this inward falling, we have to drive an explosion. So the key is that when this matter falls in, it picks up some kinetic energy because it's being pulled gravitationally and it's falling. So you're turning that gravitational potential energy into kinetic energy of the matter falling. Then it hits the shock. That kinetic energy gets turned into thermal energy, so the matter becomes very, very hot. And it gets even hotter as it settles down onto the surface of the protoneutron star. So you have extremely hot matter here. So the temperature is roughly around 100 gigakelvin, so 10 to the 11 Kelvin. And so when matter is that hot, it emits all kinds of things. Just like anything that's hot emits photons, it's going to be emitting lots and lots of photons, but it's so dense, these densities go up to maybe 10 to the 14 grams per cubic centimeter. At those densities, photons don't go anywhere. They can't escape. They're just part of the fluid. But neutrinos, because they interact so weakly, I mean, the protoneutron star is dense enough that it's still going to trap those neutrinos. But right around here, just outside of the protoneutron star, neutrinos can actually escape. So it's so hot that it's creating a huge amount of neutrinos. Those neutrinos carry a little bit of that thermal energy from here to there. By transporting a little bit of energy to here, you deposit some of the energy that's just high enough that you're able to explode the star. So the key is you have a bunch of matter lose its potential energy to make this protoneutron star. And by doing so, it puts a little bit of its energy to some of this matter, which blows up. The only way that you can do that is because the neutrinos are there. If the neutrinos weren't there, everything would just collapse and make a black hole. You would never get a supernova. So this is what it looks like in 3 dimensions. This is a simulation now that's it's starting to age. But so this is showing where's the time. So this is milliseconds after the star collapses. And so you can see this is the shock front here. You can't see, there's the protoneutron star. You can barely see it. But so around here, what you can't see is that massive, the iron core that's constantly falling supersonically inward, maybe reaching a couple % the speed of light as it's falling inward. and is falling inward, and neutrinos are being emitted from here and depositing a little bit of energy, causing this thermal turbulence to form. This turbulence pushes out bulges, and you get this very interesting asymmetrical explosion that's happening. Now this is hundreds of milliseconds, so this is all happening very much quicker than we're showing in the simulation.
Does that have rotation?
This one does not, no. So in order to do this, there's a lot of things that go into this. There's a reason why we've been working on it for decades, and we're still trying to figure out what's going on inside. So we need to treat space-time, so the fundamental curvature of space-time that drives gravity. We need to treat the unknown physics of extremely dense nuclear matter. We need to treat three-dimensional turbulent hydrodynamics, and there's nuclear reactions that are very important as well. So it's a very difficult problem.
So if you put in relativity to this, it's really about as fast as you show here. It's slower, at least for an external observer.
So this is shown as it would look for an external observer. So if you're in the frame of the fluid that's falling, you would experience a smaller amount of time, to pass through the shock. But the velocities here that are in falling, it's a few percent of the speed of light. So all things considered, it's relatively minor in terms of like the time dilation effect. But if you treat it with Newtonian gravity and compare that to the treatment with general relativity, there are differences. General relativity will tend to effectively have a stronger gravity, so you compress this core more, which means it's more compressed, which means stuff falls farther, which means you have higher energies, higher temperatures, and that can change the way the explosion proceeds. So for other types of explosions like neutron star mergers, general relativity plays a much more significant role, but it's still important in supernovae. Okay, so I do want to talk a little bit about my own particular research, because this is the canonical story that when you learn about supernovae as an undergraduate, you read the one paragraph about supernovae in your textbook, and that's your undergraduate education in supernovae. And they tell you that it's a neutrino mechanism, that neutrinos drive the explosion. But my research is I am not convinced that we actually understand this process very well. And the reason for that is that, so I told you that there are three kinds of neutrinos. That's not actually the proper way to think about neutrinos. Really, we know experimentally that neutrinos change flavor. So there's electron neutrinos and muon neutrinos and tau neutrinos. The standard model says that these are three particles just like all the other particles. You have particles, either one or the other. But we know that they actually behave in a quantum mechanical sense. So a given neutrino is in general going to be a quantum superposition of different types, and that fundamentally changes how neutrinos behave. So this is the equation that I spend all my time thinking about, this quantum kinetic equation. What it says is it describes how neutrinos move around inside of a supernova. So there's transport, so this just says that neutrinos move. They go from one place to another. There's collisions, so neutrinos absorb, they emit, they carry energy. They convert thermal energy in the gas to the energy of creating this neutrino particle. But this is the kicker part. This is the quantum mechanics that none of these supernova simulations so far have treated. And we know that this exists. This is experimentally confirmed in the early 2000s, winning a Nobel Prize. But they haven't been, this physics has not been included in supernova models for two reasons. One, because people thought they had good explanations for saying they didn't need it. Turns out those explanations don't actually work. And two, because it's really hard. We talk about the cost of a supernova simulation that we've done so far, these requiring supercomputers. This would increase the cost of simulations by a factor of about 10 to the 30. So, it's completely hopeless to just plug it in and do it. So, as a supernova modeler, of course you say, I'm going to find a way that to say that this is something that's not relevant. And for a long time, we thought that those were good reasons. But we've shown recently that there's a lot of interesting quantum mechanics that breaks that picture. So this just shows the 6-dimensional phase-space density of the distribution function of neutrinos. And so this is really a 7-dimensional equation, 6 dimensions, so 3 spatial dimensions, 3 momentum dimensions, and time. That's the equation that we're trying to simulate. We're trying to find a way to put this theory into these explosive astrophysical environments and treat all the quantum mechanics and the hydrodynamics all under the same roof. So what we have been able to do are these simulations. This is one of my simulations from a couple of years ago, showing a distribution of neutrinos extracted from one of these supernova simulations. But this is an 8-centimeter cube. So it's like something that you could hold in your hand. And the duration of the simulation was about 5 nanoseconds. Recall that supernovae, like the engine occurs on the scale of hundreds of kilometers and over the course of seconds. But we can treat this, we can do these simulations. We can learn about how the neutrinos are interacting quantum mechanically. And so what we're trying to do is map that knowledge onto into these multidimensional simulations to see how that changes the actual explosion. What I'm showing right here is the complex phase of the flavor coherence of the neutrino distribution. What that means is these essentially show wave fronts. And it looks kind of like wave fronts here. It looks like a plane wave. Wave fronts in quantum mechanical neutrino flavor change. This is showing a particular instability, which the instability that we're simulating here is the reason why we don't think that we can ignore this in supernova simulations. This is something that came to light only around 2020. So before then, this entire process was unknown. And this is not novel physics. This isn't some kind of hypothetical new particle. This is just us putting the information that we know from terrestrial experiments and saying, what if that were in a star? Just put the equations in the star. This is what it says. So that's what we're trying to do with our simulations. So how can we actually observe this? Like I said, we're anxiously waiting for the next nearby supernova. This is, once again, Super Kamiokande. These are the neutrinos that we detected in 1987 when we saw this. This is just from Super Kamiokande. If you add in the other neutrino detectors, there's about 20 to 21 or 22, depending on who you ask. If we do this, if the same star went off today, we would see thousands. Okay, so let's get back to explosion. So if we look at the largest supernova explosion, or the largest nuclear explosion that we've ever created, and compare that to a supernova. All right, temperatures. So in Kelvin, at the center of a nuclear weapon, we get something like 10 million Kelvin. Compare that to, I think this is around 1 billion Kelvin. So this is, no, about up to 100 gigakelvin or 1,000 gigakelvin. Yeah, so much larger temperatures. The total energy. So the largest nuclear bomb that was ever exploded was Tsar Bomba, about 50 megatons of TNT. 57. Okay. It doesn't fit in one line for a supernova. The density. The density at the center of a nuclear explosion gets up to maybe 200 grams per cubic centimeter. Compare that to something like 10 to the 14. The size of the explosion was maybe 35 kilometers. Compare that, I don't even remember what number that is in light years, but it's, yeah, astrophysical explosions are a lot larger. And weight, 27 tons versus, yeah, large number. Doesn't really matter how large it is, it's a lot larger. Okay, so I've explained some of the kinds of explosions that we see and some of the theory that goes into these explosions. But one of the exciting things about this field is that this isn't something that's static. Just like when we look at the night sky and the night sky isn't static, if you look closely, things are happening. We haven't looked closely enough. So there are different kinds of explosions. So this is the brightness as a function of time. So supernova 1987A versus a typical type 2 supernova versus a type 1A supernova versus this other supernova 2006 GY. If you keep looking, you'll find things that happen on shorter times and that are dimmer. In order to see those, you need to look very often, and you need to have very sensitive telescopes to see things. And we're pushing both of those limits. We do not have a complete census of all the things that are happening in the universe. And so the more often that we look and the deeper that we look, we're finding things that don't, they don't fit into any of these categories. We've created these categories of different kinds of supernovae. That's kind of an artificial imposition of our own ideas onto nature. And nature has so much more out there that we haven't discovered yet, just because we haven't looked closely enough. So here's my recipe book for different kinds of cosmic explosions, so the fireworks and nukes. Thermonuclear supernovae come from nuclear reactions of merging stars or matter accreting on top of a star. Pair instability supernova is a hypothetical type of supernova that could only have happened in the early universe. Standard core collapse supernovae are powered by gravitational collapse. Electron capture supernovae, I didn't actually talk about this one, but it's similar to core collapse supernovae, but the spark is a bit different. In hypernovae, we think maybe they're powered by rotation, maybe they're powered by some other processes. But so this is an approximate census of different kinds of astrophysical explosions. And I'm out of time. I have more details on the neutrino physics if people want to hear about it. But yeah, maybe I'll just leave that and say that it's an active, exciting field, and yeah, having me back, I'll talk about quantum computing and machine learning. Thank you.
That's impressive. Can you tell us? You're showing the evolution of each one of these entities in time. How fast they explode, or how fast they grow.
You mean this particular plot?
Yeah. Or you're simply showing how the galaxy evolved, or the universe evolved.
So this is a plot of different kinds, stellar evolution for different kinds of stars. So for the typical type 2 supernova, you have a large star that's not insanely large, just 10 to 30 solar masses or something, that evolves and forms a red giant or red supergiant and explodes as a type 2 supernova. If you have a smaller star, like our sun, you create a planetary nebula and a white dwarf. If you have two of these white dwarfs, you can smash them together and create a type 1A supernova. If you have a very, very massive star that's only possible in the early universe, you can form a pair instability supernova. Are there any that I missed? There's no hypernova on here, but it's just if you can create rapid enough rotation during this collapse, you can potentially create a hypernova. So this is just showing different kinds of stars have different final states, some of which are explosive, some of which are...
Okay. So I was confused by the scale. You actually have a different time scale in magnitude for each one of these.
Yes, yeah.
You mentioned looking for neutrinos and finding neutrinos. If I remember right, there's a lab, particle lab in the home state on it.
That's right.
At Lee, South Dakota.
Mm-hmm.
And I think it's at 3,000 feet. It's pretty high. Scary. Have they been successful at, they're using the Earth as a shield to filter out whatever particles they can. Can you comment on what's going on there? Or?
Yeah, so there's a large and growing number of neutrino detectors. Many of them will be capable of observing neutrinos coming from a supernova if it's as nearby as this one from 1987. But many of them, like that's not their main purpose. Their main purpose is doing neutrino experiments. So there's, you can look at neutrinos from the sun. You can look at neutrinos that come from cosmic rays striking the atmosphere and launching neutrinos, and you can see those. And you can also look at neutrinos that come from particle colliders. So you collide particles together, and there's a beam of neutrinos that come out, and you can put detectors at various points along that beam and show how the neutrinos quantum mechanically change flavor, which, yeah, you understand basic properties of neutrinos, which we still don't have a good fundamental description of neutrinos, which makes this an interesting astrophysical and particle physics problem. But yeah, so many of those detectors are designed to understand basic properties of neutrinos for neutrinos coming from the atmosphere or from the sun or from nuclear reactors or from particle colliders. But yeah, they're all active and they're all constantly observing neutrinos. Yeah.
As I recall, the data from that mine showed that the detected neutrinos, the flux was lower than what was expected.
Yes.
Is that because the flavor changes?
Yes, exactly. So these, many of the detectors are sensitive to only one kind of neutrino, or they have different sensitivities to different kinds. And so it's exactly by seeing how much of that energy disappears, farther away from the source, you're able to say, it's not that the neutrinos went somewhere, it's just that they became invisible. And so the same thing can happen inside of a supernova. So if you have a neutrino that would have deposited energy to cause an explosion, but instead it changes into a different flavor and keeps flying, that's a problem for the explosion. So yes, it's the exact same thing. So these neutrino experiments are deeply tied to the physics that we're trying to put in these models.
Can you tie the invisible neutrino expected quantities to dark matter?
Potentially. There's some parameter space for neutrino dark matter. It's, the name of the game for dark matter, it's never been detected, so that there are many experiments that are all sort of chipping away at this parameter space of the mass and the interaction strength of particles. It's difficult to make neutrino dark matter, but the possibility is still there.
That's great. Thank you very much.
All right, thank you.
Okay, I'd like to.
Can you hear me now? All right. Well, I'm going to talk about the eclipses this year, 2025. There are going to be 4 eclipses this year. What normally happens during the year is 2 eclipses are solar eclipses and 2 of them are lunar eclipses. It's going to be, the 2 solar eclipses are going to be partial eclipses, and the 2 lunar eclipses are going to be total eclipses, total lunar eclipses. And there's going to be no total solar eclipse this year. It was one last year, but there's going to be one this year. The first eclipse is going to be in March. It's the 14th of March, and it's a total lunar eclipse, and it's going to be visible from here, from Tennessee. Actually, from all the United States and from all Americas, North and South America. The next eclipse is going to be a solar eclipse. It's a partial one. It's going to be the 29th of March. So it's also the month of March. It's 2 weeks after the other one. It's going to be visible from some parts of the US, but not from Tennessee. So the only eclipse going to be visible from Tennessee this year is going to be the total lunar eclipse of the March 14th. Then in September, it's going to be another total lunar eclipse, the 7th of September. It's not going to be visible from here either. And then finally, it's going to be a partial solar eclipse on the 21st of September, and it's going to be also in the other side of the globe. It's not going to be visible from here. So the next one, the total solar eclipse of March 14th, is a lunar eclipse is going to be during the night. The solar eclipses are during the day, the lunar eclipses are during the night. The time of the eclipse is kind of a little inconvenient for some of you probably. It's going to be, as you can see, it's going to be seen from North and South America. It's not going to be seen from the other side of the Earth there. It starts with a penumbral phase that is going to be 3 minutes before midnight. And then the partial phase, which is when the moon gets into the umbra of the Earth, that's going to be at 1:09 a.m. And then the totality starts at 2:26 and ends at 3:31. So the total eclipse is going to be 1 hour and 5 minutes between 2:26 and 3:31 a.m. Then the partial eclipse ends at 4:47 a.m. and the penumbral eclipse ends at 6 a.m. The penumbral phase is not very spectacular, but the total phase is going to be very nice. So I recommend that you have a chance to look at this. If it's not cloudy, of course, because the weather here is not very nice. When we have eclipses and things like that, the clouds come, so we don't see the thing sometimes. So if it's going to be cloudy, then you don't have to get up during the night. You won't see anything. But if it's clear, I think it's worth it to see it. It's going to be a good one. And it's the only one that you are going to see this coming year, okay? So,
Is that daylight time, or is that going to be daylight savings time?
it's the time for here, for us.
Okay.
The times you have over here are universal coordinated time, which is the time from Greenwich. And so you can convert that to the time from here, and it will be the times that you have over there. Okay, so these are the times for us, for here, for East Tennessee. And here you have two pictures. Before the eclipse will be a full moon, and it will be like this. And when it gets into the eclipse, it gets, instead of getting completely dark, it gets like red, and different kinds of red. Every eclipse is different, so it's worth it to check it. And you know why it gets red, right? Because the light has different colors. It has the blue, it has the red, and the red reflects around the atmosphere of the Earth, and then it gets into the moon. So it doesn't get completely dark, it gets red. And this is another view of the different phases of the eclipse. You start with a full moon over there, and it gets partial like this, and then it gets total like that. And then goes again into a less totality, and then it goes all the way to the other one there. So it's worth it to see this. It's a nice one. Okay, the next eclipse is a partial solar eclipse, and it's visible. It's a partial one, so it's only the maximum occultation of the sun is going to be 93.6%. And it's going to be over Canada, over that point over there, north of Canada, over the Labrador Peninsula. But it will be visible still for some parts of the US. From the Washington, D.C., only 1%, and from Baltimore, 3%, Philadelphia, 10%, and New York, 20%. Now, from Europe, from Italy, you can see between 0 and 20%, in Spain, between 20 and 40%, in the United Kingdom and Ireland, between 40 and 60%, in Iceland, almost 80%, and in Greenland, between 80 and 90%. And again, in the United States, you can see some. I'm going to show you this here. This is another view of the area of the eclipse. So you can see from this area over here, you can see some part of the eclipse at the beginning, when the sun rises in the morning. The maximum eclipse for 93% is in that point over there, over the Labrador Peninsula in Canada. So then here is the area of visibility from the United States. So it's parts of Maryland, Pennsylvania, and those other states over there. Nothing from Tennessee. Okay, the next eclipse is going to be a total lunar eclipse, and that's going to be in September 7th. And as you can see over here, there is nothing to see from North or South America. You have to go to India or China to see that. So I guess probably if you are going to be interested in seeing that, I can give you more information, but otherwise I think this is not going to be of too much interest for us. And finally, this is last eclipse of the year. It's going to be a partial one in September 21st. The maximum cover of the sun is 85%, and it's over here, in this point over here. It's between Antarctica and New Zealand. So it can be seen from New Zealand, Antarctica, and the islands over here in the Pacific Ocean. So these are the 4 eclipses this year. And I have some also a little information more about the other interesting astronomical events in this month, in the month of February. The full moon was last month, January 13, and it was also an occultation of the planet Mars by the moon. That was last Monday, and it was totally clear I was able to see it. That was an interesting thing. It's like an eclipse. The moon covers the planet Mars. Yeah, so it was something like this. So you see the planet Mars was over there and the moon covered it, and then it came out from the other side. That happens at about 9:05 p.m. and Mars came out from the other side about 10:15 p.m. And the other thing you're going to see this month is all the planets going to be aligned and visible in the evening and the night sky, and also the moon will be there. And as you can see, these are all the planets that you can see. Mercury cannot be seen in the morning, in the evening this month, but it will be visible next month. So next month you can see all the planets. Of course, Neptune and Uranus need a telescope to be seen. The other ones you can see them with the eyes, without any telescope or binoculars. So in the morning you can see Venus, Saturn, Neptune, Jupiter, Uranus, and Mars. I mean in the evening, excuse me. And in the morning, Mercury this month. And then next month you can see all the planets. And of course you can see the Earth all the time. Right? So this is, in February 4th, you can see all the planets except Mercury. And then this is in February 13th. You can see all the planets now. The first one there is Mercury, then is Saturn, Venus, Jupiter, and Mars. And this is another view on February 20th. So you can see all Mercury and Saturn, they are very close to the Earth. This is in the evening, and then Venus, Jupiter, and Mars. Anyway, this is all I have to show. Thank you.